Hello everyone and welcome. My name is Masaaki Terai. I'm a R&D scientist at Riken RCCS. Today I will talk about a study of operational impact on power usage effectiveness using facility metrics and server operation logs in the K computer. This material was recorded for Virtual Workshop EEHPC SOP in September 2020 in conjunction with Cluster Conference. Let me introduce this project quickly. This project has started since the last May as a preliminary study for power and cooling system efficiency in data centers. Fortunately, we have already 7 years completed computer operation logs. However, while data is ready, we have not performed analysis often enough though. In the following slides, using that data, I'll talk about PUE-based evaluation in the official service period of the K computer. And then, we will show 3 cases in the rest of the slides. I know today most of the people are interested in Fugak than K computer, which was replaced. However, Fugak still being developed, we don't have enough data at the moment. Therefore, this material focuses on the operation of the K computer period. We believe such a historical survey is valuable. Let's get started this material from the background. Today, power consumption is one of the significant issues in supercomputing centers as well as data centers. Maybe it directly linked to the budget. In fact, no data centers can provide any services without electricity. At the time of K computer, power consumption was about 15 megawatt on average. Time have changed. Today at the Fugak period, power consumption reached 28 megawatt in the top 500 benchmarks. Energy efficiency operation becomes a more significant issue than it used to be. By the way, the operations mostly depend on facility experts, for example, electricians, boiler engineers, and so on. Their expertise, in other words, know-how, find a solution for a specific problem. However, it requires trial and error process, and the solution is often very obscure how much the solution is optimized. On the other hand, enormous computer systems like the K computer and facility commonly produce various types of data. We believe that their abundant expertise is buried in the data. For the past several years before this project started, my colleagues have struggled to collect various types of operational data. In this study, we used 2 types of data from that, specifically server operation logs and facility operation metrics. As I mentioned before, comprehensive analyses with PUE in the entire service period are not performed enough. One of the obstacles is that the measurement data are scattered across equipment because data analytical infrastructure is experimental phase. On top of that, part of data still used in the form of an unstructured file based on paper document, or the data use a simple CSV format at best. We know there are so many problems. To resolve those, we understand the analytical infrastructure is paramount. However, it is outside the scope of these slides because we'd like to purely review our operations in the official service period, especially regarding power consumption and cooling behavior. So we will focus on analysis with the data in this study. Based on the background as I mentioned in the previous slide, we can organize the objective as follows. 2 stable and energy efficient operations over the next decade. Understanding the historical facility behavior of the K computer is variable. It means we study past events based on data, reveal facts, and reflect them to our operations. At the moment after Fugak preliminary operations started, this study resembles a historical survey process. Points are following. In this study, prior to a detailed study of the power and cooling system behavior, we evaluate PUE-based energy efficient operations as a preliminary study. These analyses are performed throughout the entire K-computer official service period with modified PU metric, which has been proposed by the government departments and agencies worldwide. Further, the analytical infrastructure is related to context and should be considered in the future work. We already introduced the K-computer specifications in several meetings. This is our review slide, and let me introduce the information quickly. The K-computer is the first 10 petaflops supercomputer for general-purpose computing without GPU-like accelerators. The official service period was from September 2012 to August 2019. The service duration was about 7 years. It consisted of 864 compute racks and peripheral systems, including petabyte-scale file system racks. Facilities consisted of cogeneration system, chillers, circuit breaker, air handling units, and water cooling system. At the moment, all the compute racks in the K-computer were replaced by the successor new systems rack. However, most of the K-computer's peripheral equipment has been enhanced and is being used as part of the Fugaku infrastructure. One of the noteworthy mechanisms in the K-computer facility can be found in the power supply and cooling system. So in this slide, we focus on power supply system. The entire center is powered by two energy sources. One is purchased energy from the electric utility company. The other one is generated energy by gas turbines installed on the premises. First, the purchased energy is received by the substation. The substation can receive up to 30 megawatt electricity from a utility company. Actually, during the period, it supplied 11 to 12 megawatt on average. On the other hand, there are two CGS. One CGS gas turbine engine can generate up to about 5 megawatt electricity. During the service period, they usually worked alternately. When one CGS is active state, the other one is standby. This is a summary slide to show history of power consumption in RCCS for the past 7 years. It covers the entire official service period. Green line denotes total energy in the center. As you can see, during the service period, the total power consumption in all facilities reached nearly 15 megawatt-hour on average. Red line indicate all the IT equipment, including servers, storage systems, and communication devices. The power consumption of the IT equipment accounted for approximately 80% of the total use. Of course, the IT equipment includes the compute nodes, and their consumption was dominant in the total use. The rest of the usage includes auxiliary consumption of the cooling equipment and the research building. The rate of on-site generated energy to the total energy is about 25%. The CGS kept long-lasting operation without critical failure and generated constant energy around approximately 4 megawatt hours throughout the service period. We will explain power usage effectiveness, as known as PUE, as a metric with a few slides. As you know, PU metric is widely used to assess and improve data center performance in terms of energy efficiency. This metric is a ratio of total energy usage to the IT equipment energy usage. Usually, the metric value may be more than 1. Assuming that the power consumption of all the facilities could be reduced to 0, which is the ideal situation, then PUE will converge to 1. The total energy term in the numerator can be divided into two terms, IT equipment energy, and facility energy. In most cases, the power consumption of the cooling system is dominant in the facility energy term. Generally, improving data center facility efficiency tend to be a core competence for any service provider. Therefore, many data centers and supercomputing centers frequently evaluated the metric and published it in the context. The price of the external power supply is a cost that the data center cannot control. As one of the solutions, data centers attempt to optimize their operations based on their environment conditions. For example, power supply cost, uh, availability of natural resources in the region, government policies. There are so many incentives to optimize their operations. Actually, RCCS uses two energy sources. Eventually, diverse optimization efforts make it difficult to compare centers equitably. Due to the situation in 2012, in 2011, in order to measure PUE equitably in data centers that depend on several types of source energy, the group of global leaders consisted of the United States and Japan's government departments and agencies, and European Commission's Joint Research Center proposed new measurement protocols for PUE. We understand the protocols as a standard and use it in this study. In the protocols, source energy is frequently appeared. I believe that source energy and site energy are key technical terms to understand the concept of the modified PUE. In my understanding, building energy management has so many similarity to data center's energy management. This formulation seems to be based on the energy efficiency benchmarking in building management. They usually use multi-energy sources, for example, purchased electricity, coal, coke, fuel oil, and natural gas. And they require an equitable evaluation method for total energy use from raw fuel that is burned to create heat and electricity. According to the protocols, to make compatibility between the original PUE and modified PUE, the protocols introduce a correction coefficient called source conversion factor. The coefficient excludes the efficiencies of generating electricity from the modified PUE. In other words, the factor corrects the ratio of the weighting factor in the formula. As you can see in the figure, the original PUE and modified PUE are the same. That is, if conversion factor is constant value, the modified PUE metric includes generating efficiency of electricity. In these slides, to reveal generation efficiency by using the feature, we assume that a conversion factor is constant. By the way, in our confirmation, conversion factor is calculated roughly at 1.1. As a result, if the conversion factor is assumed to be 1, usually modified PUE is larger than the original one. In this slide, we will explain metrics used in this study. We used two types of historical hour timescale data collected by the system. Facility operation metrics includes various physical quantity, for example, power consumption, gas consumption, amount of purchased electricity, and on-site generated energy. We call those facility operation metrics. Meanwhile, the vendor company submits monthly reports compiled from various types of daily events. For example, machine failures, file system problems, plant outages, and various maintenance events. The server operation logs were extracted from the reports. Each event record includes date and time pair, indicating the beginning and end of the event, as well as details about the event, In this study, we classified the events in the logs as annual maintenance event, emergency maintenance event, and large job period event. The entire service period is about 61,000 hours. By the classification, the annual maintenance event is 3,347 hours, consisted of 95 events. The emergency maintenance event is 24 hours, 97 hours, consisted of 81 events. The large period event is 3,951 hours, consisted of 81 events. As you know, PUE is a naive metric because the value increases rapidly and diverges when all the computer nodes stop due to non-electric outage. To calculate PUE more precisely, we attempted to exclude metrics of the maintenance events in the PUE calculation. As you can see in the figure, we can easily understand the change of metric along with operation contexts. By the way, in this study, the analyses were based on hourly temporal resolution. However, if there is an event with a specific time information that is missing value, we treat the record as a full day event. Due to the reason, a duration between different event types are allowed to overlap. This slide shows monthly average PUE values in the entire service period. This monthly average PUE roughly ranges from 1.33 to 1.55. To determine a baseline, we evaluated the representative value using a monthly average of the as-is data. The minimum and maximum PUE values are 1.339 and 1.547, respectively. The average PUE is 1.398. Next, let's see the operation impact for each event type. The PUE excluding annual events is 1.395. When both types of maintenance event are excluded, PUE is improved to 1.393. Further, when all events are excluded from the as-is data, PUE is improved to 1.392. From the result, we found that the annual maintenance events have the most impact on PUE in the three event type. Based on the results, while they perform some effects as a kind of noise, the impact of the operational events on PUE is not significant. In my understanding, long-term sampling period may reduce the noise caused by the maintenance events. If PUE based on short-term sampling is used, or if a more precise PUE is required, operational events should be considered. This is a summary slide to show history of PUE for the past 7 years and compare PUE metrics between event types. By the way, we don't use color mapping to indicate maintenance events in this figure because there are so many maintenance events throughout 7 years, and then the background colors are too dense and flooding. That feature will be used in detailed investigation in the next slides. Back to the context in this slide. At first glance, the PUE roughly has trended down from 2012 to 2019. Meanwhile, part of PUE values changed dramatically with sharp downward peak and then a rapid upward change in the 12 months. We can find the phenomenon in April 2014 to March 2015 and in November 2017 to December 2018. According to the facility operators, some operational experiments in CGS were performed in the period. Between as-is PUE and event-excluded PUE are often significant differences in around every April and October, because in April There were often long maintenances prior to the new fiscal year period. That month especially spends long-term annual maintenance operation compared with the rest of the months. Also, in October, there was often planned outage to comply with the law. It spans about a week every year. Those can not explain all the phenomena. However, we can understand one of the phenomena along with the operational context. To show metric behavior in more detail, we choose three cases which correspond to the red square in this figure, and we will show those in the next slides. This is a first case to show a time series of daily average PUE over a year. This figure is based on April 2014 to March 2015. During the 12 months, the PUE metric dramatically changed, as you can see in the figure of the previous slides. Yellow background color means an annual maintenance event. Gray color means a large job period event. Red background color means an emergency maintenance event. FYI, as you can see in this figure, the maintenance events periodically appeared along with the events. Per consumption tend to be decreased and PUE tend to be large. In particular, in early July 2014, there was a long-term annual maintenance event that caused the downward peak in power consumption. Totally, regarding power consumption, the effect of annual events was relatively greater than other types of events. In addition, the on-site generator had constantly produced 5,000 kilowatt-hour energy since July. After August, the generated energy decreased to approximately 2,500 kilowatt-hour. Along with that change, the PV metric increased from approximately 1.375 to 1.425 and then maintained an almost constant value. As a principle, total power consumption in the entire center was constant. That is, when the gas rate increased, the purchased energy decreased. Intuitively, gas consumption and the amount of generated energy have relevance. Also, based on the formula of the modified PUE, it depends on the amount of gas consumption. From that, a high rate of generated energy compared to purchased energy seems to be one of the conditions associated with maintaining lower PUE. This is another case to show a typical operation month in November 2016. This month had only types of annual maintenance and large period events. That means it is a typical example for stable operation month. As well as the previous slide, we used background colors to indicate event types. As you can see, power consumption decreased approximately 24 hours before entering scheduled large job period. This behavior is reasonable because it causes the job scheduler's policy that postpones most workloads to prepare unallocated compute nodes. After entering the period, power consumption appears to increase depending on the workload. In the period, PUE temporarily increased due to the rapid change of the source energy ratio in the annual maintenance event. This rapid surge of the PUE metric makes noise and motivates us to exclude maintenance event periods from PUE calculation. This is also another case to show typical CGS operation with detailed hourly metrics in April 2014. The top figure shows CGS generating energy and calorie. The calorie is converted value from amount of gas consumption to energy multiplied by weighting factor based on the protocols. The Middle figure shows CGS generating power based on hourly measurement. The bottom figure shows hourly PUE. According to the sub-operation logs, this month includes a large job period that began between April 8 and April 9. Unfortunately, time information of those event data are missing. Thus, we use to we use those records as a full day events. From the middle figure, the period of the simultaneous power generation by two CGS is in preparation for the large period. However, even though two CGS worked simultaneously, the total energy was lower than the energy in the rest of the months, and the PUE metric became worse. We also focus on that the PUE metric spiked on April 23rd. On that day, the operation switched the main generator from CGS number 2 to number 1. The modified PUE with constant conversion factor detects a change of CGS operations. We believe that there is an operational issue associated with simultaneous generation by CGS. One reason for this issue is that the facility design imposes operational limits. However, determining the cause based on the result is difficult. We believe additional studies are required. This is a summary slide. I will quickly conclude. In these slides, we showed PUE-based evaluation in the K-Computer official service period as a preliminary study. If you have any questions, hopefully I will answer them as a workshop. Thank you very much.